Do you hate me yet? No? So let me continue and let me try to finish. I mean, we don't have much time. We still have an hour and a half. So I'm going to finish with the alchemical transformation, and I'm going to talk now about maybe what you all have been waiting for, binding free energies. So you may be familiarized with this kind of setting, this kind of contraption, which is oftentimes referred to as high throughput virtual screening. So the idea is the following. The idea is you have a certain target, protein. So again, I'm putting the neuraminidase, and you're trying to find a drug candidate for this particular target. And so you have a library of drugs, either virtual or real, and pharmaceutical companies have huge libraries. And then using these filters are nothing else than methods of increasing sophistication. So you start with shape recognition, which is extremely fast, to discard a lot of, poor candidates. And then you go to rigid docking, and then you go to flexible docking, and finally you go to the most expensive calculation, which are the fringe calculations. But the idea is at every step of the way, the computational investment is constant. So you're doing a lot of cheap calculations or a few very expensive calculations. But in the end, you want to use fringe calculations for the best possible candidates to establish some kind of a ranking as a function of their affinity for the target. So what I put here on the right-hand side are some excerpts of articles that were published in 2000 and more recently 2013. All the way to 2000, pretty much free energy calculations were seen as kind of a promising way to basically replace wet lab. So you would basically be able, with free energy calculations, it was kind of oversold, let's face it. You would be able to predict binding affinities with number crunching. And then came the realization that it was not that simple. And it was not that simple for two reasons. First, there was the computational investment. I mean, sampling for a long time was an issue, and especially when in the course of binding you have a lot of conformational changes, reorganization of the host, reorganization of the guest, and that is not always easily captured by molecular dynamics. The other reason is, of course, the force field. So you already heard about force field, or maybe you will hear about force field. This is still a problem, actually. Having a good force field for proteins, but also a good force field for small molecules. And let's face it, I mean, the force fields that we're using are very primitive. I mean, if you're thinking in terms of the macromolecular force field that we're using, which basically rely on the pairwise additive approximation, so that are bereft of induction effects, and they're very simple in terms of electrostatics. They're just using charges, so it's kind of a problem when you have atoms that have like lone pairs, and so have like a big atomic quadrupole. So describing a quadrupole with one charge is kind of dangerous, to say the least. And then polarization effect sometimes can be very important. So it's true that these force fields are very rudimentary and kind of plague the accuracy of the fringe calculation. So today, even though number crunching is less of a problem, and for different reasons. First, because we have access to more powerful, massively parallel architectures. there are still some issues. I mean, there are, so algorithms have also kind of improved. So you have like variants of FEP calculation. You may have heard of REST. Replica exchange really helped like for improving the ergodicity of the sampling. We're going to talk about that in the end of the lecture. But force field is definitely a problem. That said, it's important to establish gold standards for this calculation. And these gold standards can be established using, I would say, a paragon for protein-ligand binding. And basically, the example that I'm going to show you, we're going to basically sweep under the rug the problem of the force field. So we're going to assume that the force field comes from God, and in this case, God is Martin Karplus and the John. So you could think of the protein-ligand problem from a brute force MD point of view. And this is a movie from a simulation that was done by Gianni De Fabritis in Barcelona. So they basically run many simulations, independent simulations, looking at binding events and unbinding events. I think that they didn't see any unbinding events. Maybe I'm wrong, but that needs to be checked. But potentially, assuming that your binder is not too strong, I mean, you should be able to see if you run long enough. And I think in that case, they were running 500 independent simulation of 100 nanoseconds each. So if you have enough statistics, you should be able to get enough off events, so unbinding events, and on event binding events, so that you can get you can approximate the dissociation constant that you need, which is readily comparable to experiments. So from Biacor, surface plasmon resonance experiment, or ITC, isothermal calorimetry, which gives you the KD. Basically, what we're after is this equilibrium here. So protein plus ligand in equilibrium with the ligand bound to the protein. So what I'm going to show you now is maybe a different way to approach the problem. So not brute force MD, but using free energy calculations in the context of alchemical free energy transformation. So what's the problem? What are we talking about here? So we have a box of water with a protein, and we have end ligands that are floating around the protein, and one of the ligands is actually bound to the protein. So we're going to introduce two probabilities: P0 that the ligand is not bound to the protein, and P1 that the ligand is bound to the protein. So we can rearrange rewrite the equilibrium constant, introducing this P1 and P0 probability, and then we're going to expand them, introducing some configurational intervals. So I'm gonna introduce two subscripts. I'm going to introduce the subscript site and the subscript bulk. So if I say site, it means that the ligand is bound to the protein. And if I say bulk, if I write bulk, it means that the ligand is floating in the bulk far enough from the protein. So as you can see here, we have a combinatorial. So the first ligand is bound to the protein. Then here, the second term, the second ligand is bound to the protein, and so on and so forth. But of course, the ligands are indiscernible, right? So we can kind of factorize and put like an n in front of the integral, because we have n ligands. And we will now also write that the concentration in ligand is equal, because it's a kind of a homogeneous environment, that the concentration in ligand is equal to n divided by the volume of the bulk. I'm going to also introduce this Dirac function, saying that if my ligand is not bound to the protein, I assume that it's lying far away at some position x1 star, so that it does not interact with it doesn't see the protein. And so in the end, I'm getting this equilibrium constant, which includes this Dirac function. As such, I can't do much with it. Certainly, from the point of view of molecular dynamics, I cannot do much with it. And I'm going to show you now that we can take these two different routes, the alchemical route and the geometrical route, to actually make something useful. So for the alchemical route, because we are in the alchemical chapter, we're gonna look at this equilibrium here. Went a little bit too fast, but so the idea here is the following, and that goes back to original work from Jan Hermans. Maybe I should replay this slide. I want your attention to focus on the thermodynamic cycle here, and also on this little box here. So the idea is we're going to do alchemical transformation. Alchemical transformation, we're going to make the ligand disappear on the left-hand side in the unbound state, the free state, bulk state, on the right-hand side in the bound state. Now, I would like to draw your attention to this little animation, which we call the floating ligand problem. So what's happening is when I do my transformation whereby I decouple, I annihilate the ligand in the bound state. So when I decouple it, basically I kind of loosen the interaction energy, and so the ligand starts to float away. Per se, it's not a problem. It becomes a problem when I want to do the reverse transformation, the creation transformation, because now the starting point is the ligand being far away from the protein, and the chance that when I recouple the ligand to the protein, it will never reappear where I expect it to be, right? Therefore, violating the principle of thermodynamic micro-reversibility. So our philosophy is if you cannot simulate it, restrain it. And that's what we're going to do here in this cycle. So when I put a little 0 here as the superscript, it means it's the free ligand. If I put a star, it means it's a restrained ligand. So what I'm going to do here in this thermodynamic cycle, before I actually calculate the true alchemical free energy, which is the annihilation going in that direction, or the creation going in the upwards direction, I'm going to impose some restraints. I'm going to restrain the ligand in its native conformation, in the protein-ligand complex, in its native orientation, in its native position. So how do we do that? Sorry. So how do we do that in practice? So we have the protein, we have the ligand bound to the protein. We're going to first freeze the conformation of the ligand, and then we're going to introduce some groups of atoms in the protein and in the ligand to define the position, the orientation of the ligand with respect to the protein. Okay. So restraining the position, restraining the conformation, we do that with an RMSD. Restraining the orientation, we do that with the Euler angles, the 3 Euler angles, and defining and restraining the position, we do that with the usual spherical coordinates. So r, theta, and phi, the polar angles and the distance. And only then I can make my ligand vanish in the bound state. And of course, in the bulk, the only thing that counts here is the conformation. So to summarize, I would have to do a decoupling or 2 decoupling transformations. So I have to decouple the ligand from the protein in this system, right? And I also have to decouple the ligand in the unbound state in this system, the bulk state. Okay, so those are like the green transformation. And then, because I have imposed some restraints, so that the ligand is in the native conformation, the native orientation, and the native position, Well, all of these restraints basically contribute to remove some configurational entropy, right? So this configurational entropy actually contributes to the binding free energy. So that I have to take into account. So I need to calculate the contribution due to these restraints. So this is what you have here in orange. And then what are these purple terms? Well, I need to balance what I'm doing on the left-hand side of my thermodynamic cycle and what I'm doing on the right-hand side. So on the right-hand side, in the bound state, I have this orientational contribution for the restraints and this positional contribution for the restraints, right? For the bulk, well, I also need that, therefore. So what I'm doing is, but in the bulk state, we're just talking about translation and rotation, tumbling of a rigid body in a bulk environment. And this can be calculated analytically. So that's the usual integral of r square d theta dr d theta d phi r square sine theta, and that's it. So I just integrate that. So I introduce the solid angle and so on, and that's pretty straightforward. Okay, but so that's the difficult part. Maybe you want to do things a little bit easier. So as you can see in this animation, we are in the cavity of neuraminidase, and we are transforming one drug into another one. We're transforming Tamiflu into Relanza, which were the blockbusters that were used to fight avian flu. So in this case, we look at this, we consider this thermodynamic cycle to calculate the relative binding affinity. So we're no longer interested in the absolute quantities, which we just calculated in the previous slide. We are actually interested in these quantities. So the transformation of ligand A into ligand B in the bound state and in the unbound state. And so the difference, the delta delta G, the difference between this one and that one, actually, yeah, that's right. This one and that one is equal to the difference between the horizontal lengths. Okay, and that's much easier to carry out. That's cheaper. It's particularly well suited for congeneric compounds. So if the compounds are very similar, and you just change one decoration, let's say you add a CH3, you replace a hydrogen by a CH3, or you replace an OH by an OCH3, or that's like the best method for it's fast and usually it converges pretty quickly. Sometimes, especially when there is a change that the binding pose may change, you may need to introduce some geometric restraints. And of course, then you will have to calculate the contribution of these restraints to the delta delta G. Now, what you can do for the guest, you can also do for the host. And so imagine that you have a protein and you want, and this protein binds a certain ligand, and you want to see the effect of a mutation, a spontaneous mutation. Actually, this is what we looked at for neuraminidase, because neuraminidase, well, the virus at some point, by some combinatorial effect, thought that maybe it should change, it should evolve, it should mutate to resist to one of the two drugs. So we found out that there were some mutations, spontaneous mutation, that made it completely, that made Relanza completely innocuous to the virus, but Tamiflu was still effective. It couldn't, actually a single mutation couldn't annihilate the effect of the two drugs at the same time. So in this case, what we do is, again, what the mutation is, we mutate the protein, so we change one amino acid in the unbound state, and we change the amino acid of the protein in the bound state. And again, we calculate the delta delta G. Okay? So far, so good? Okay. Okay, so now, how about entropy? So this is a free energy calculation lecture, but sometimes you can get the entropy for the price of the free energy calculation, or slightly more. So there's a paper by the Corpus group from the beginning of the 2000s, but actually take the 20-Landau expression of the free energy and kind of restate it, rewrite it, and to get the delta S. Now, as you can see, if you do that, and the expression, of course, is a little bit more complicated, but most importantly, you introduce these averages here, this average of U0, and let's face it, I mean, this converges much slower than the average of a difference. So these calculations, I mean, entropy calculations usually are prone to convergence issues because now you're not just considering the perturbation, but you're considering also the entire energy. So it's not just, so imagine that you're doing protein-ligand. It's not just about the protein-ligand interaction, which is embodied in the delta U. It's also U itself. So it means like the protein, the ligand, and their environment. So in that, you're throwing all the solute-solvent and solvent-solvent interactions. And that converges very slowly. So if you look here, this is the hydration-free energy of, if I remember correctly, of methanol. Yeah, that's methanol. So what you have here is the free energy. And as you can see, after 8 nanoseconds, we have converged after 8 nanoseconds. This is the experimental value. This is what the force field gives you. Force field not quite there, but it's not too bad. But if you look at the calculation of the internal energy delta U of hydration, or of the entropy minus T delta S, you have to invest quite a bit. Of course, I mean, this is still cheap by comparison with big simulations of proteins, but still, I mean, compared to the free energy, you have to invest quite a bit. I mean, we're talking, in this case, of a factor of about 10. It's 10 times more expensive to get, in the particular case, I don't want to make that a rule of thumb, but in this particular case of the hydration of methanol, it's about a factor of 10, the computational investment to get the entropy. There is an alternate route. I think one of the first simulations was done by Ron Levy. And in this case, what you have to do is to run different free energy calculations at different temperature, and then you use the linear approximation. So you calculate the delta S is a finite difference. So basically, the free energy at T1, the free energy at T2, divided by the different T2 and T1. Okay. One of the exercises, I think that's one of the exercises that you will have to do, is to study hydration of a small solute. So this is the case of ethanol, and the way we do it from an alchemical point of view is so we make it disappear, or we make it appear in the vacuum state and in the aqueous state to complete the thermodynamic cycle. So so the setup is very simple. So you have your box of water with your ethanol, and progressively, using lambda, from lambda equals 0 to lambda equals 1, you make it disappear, and you make it reappear. Why do I need to complete the full cycle? So why do I need to calculate, actually, why do I need to do this transformation in vacuum? Does someone have an idea?
Solvent.
What's that?
The effect of the solvent.
Not quite.
So this summation of all the delta G's have to equal 0.
Yeah, that's kind of a tautology. I mean, that's yes, you need to complete the cycle. Yes, that's. But why do you need specifically to do it, to do the transformation in vacuum? You could, for instance, and that's actually hidden in this variable here that is available in lambda. I'll decouple off, I'll decouple on. You could basically, that controls the non-bonded interaction. If you put alk decoupled on, it means that you will ignore the change in the non-bonded interaction. The intramolecular non-bonded interaction. You ignore them.
Well, I mean, you don't know the path in water. So, like, if you go from vacuum to water, you're just adding water to the system, but you can have a different path if you're going from.
Not quite. No, it's really an intramolecular question. Okay, I'm going to take myself a chocolate and then I'll give you. So the reason is very simple. If you have a very rigid molecule, it doesn't matter because whether you are in vacuum or in water, it's rigid, so it's not going to change its conformation. But if you have a very flexible molecule, that's a different story. So remember the Onsager law that relates the electrostatic free energy to the dipole moment of the molecule. It varies as the square of the dipole moment. In other words, if you are in vacuum, the molecule will adopt a conformation that minimizes its dipole moment. Whereas when it's in a high dielectric, high permittivity environment, it will adopt a conformation that maximizes its dipole moment. In other words, in vacuum and in water, you will have very different conformations, therefore very different intramolecular interactions. Assuming that you have the same intramolecular interaction in water and in vacuum is just wrong. Okay? That's why you need to do both.
That will be the case of most of these calculations.
That will be the case of most of these calculations. Okay. Another thing that I would like to draw your attention to is when we say we do the calculation in vacuum, this is not exactly vacuum. We're still doing that in a lattice. We're still using a lattice. To be fully compatible, this lattice should have the cell should have the same size. To be consistent, to be congruent with the calculation on the right-hand side, you want to have the box size. It's a box, it's a real box, except that it's an empty box. It only contains the solute. But you still have the interaction of the solute between the cells. Okay. And so if you do that, then this is what you get, and then you can do your annihilation, you do your creation, and then you can combine the statistics of the two to get the bar estimator, and get minus 4.4, experiment is minus 5.1, voila. So, just like in any experiment, as a good practice, you want to accompany your free energy calculations, the result of your free energy calculation with an error estimate. And you should make a distinction between statistical and systematic error. There are two sources of errors in the free energy calculation. Errors coming from statistics, that's usually the variance, and error coming from the so-called systematic error, which is everything else, like simulation, the finite length effect of the simulation. The force field, that's systematic. Let me give you an example, just so that you see the difference. Imagine that you have a solute that is flexible. And let's say that, to make it simple, let's say that this solute can assume or adopt two distinct conformations. But its two conformations contribute importantly to the hydration free energy. And you want to calculate the hydration free energy. The problem is that in the course of the simulation, because the torsional barrier is too high, and you don't do anything special to actually promote isomerization, in the course of a standard length simulation, you will either see this conformation or that conformation, but you will not see the isomerization occur. So, in terms of statistical, so you can do a pretty long simulation, still be stuck in that conformation. In terms of statistical error, you will do a pretty good job because the statistical error will reflect your ability to sample all the configuration of the solvent around the molecule, around the solute of interest. Right? And for that, you're doing a good job. You're doing a lousy job in terms of systematic error because your simulation is too short and you will never see the other conformations. So your free energy will be erroneous because you're missing an important contribution by not sampling the alternate conformation. You see the difference? So from a statistical point of view, nice. From a systematic point of view, lousy. But that can be solved. I mean, there are options. I was talking about REST. REST is an algorithm exploiting replicas to help you actually cross the barrier. You can use Benoit Roux's boosting potential. So the boosting potential is you do a separate free energy calculation whereby you estimate the torsional barrier and you feed this torsional barrier in the course of your FEP calculation, and so your molecule will keep isomerizing in the course of the simulation. So you will sample both states, and then you just unbias because this is a bias that you've introduced in the calculation. So you need to remove it from the a posteriori. You remove this bias. So there are different ways to estimate the systematic error. I don't want to go into the details, especially we don't have much time. But I'm more than happy to answer questions this afternoon if you're really into this. You want to stratify. Now I think that you're all convinced that you need to stratify to reduce the variance and improve the overlap of your ensembles, and you want to combine forward and backward simulations to reduce the variance and get the maximum likelihood estimate. Last thing, this is a very good example. I wanted to show that because this plugin exists because of you guys. This was born actually in a very similar workshop in Atlanta, and the combination of having a heterogeneous audience of experimentalists and theorists allowed to do that. We had people from experiments, and they were very interested in free energy calculations, but they didn't want to know the fine detail of the free energy calculation, and I can understand that. I mean, this is your job, this is my job. We have different jobs, different specialties, but they wanted to be able to predict the effect of alanine point mutations, which you can use. They are called in general alanine scanning experiments. You can use them in the context of protein substrate binding. So in this case, you mutate in the protein some residues that are interacting with the ligand and see what are the important residues contributing to the binding. Or you can use them in the so-called TSAs, thermal shift or assays, to see if some mutations are prone to destabilize the protein and take the protein towards an unfolded state. So what we did is we actually built this piece of this plugin that is now part of VMD, and you can just enter your PSF and PDB file, and then you select the amino acids that you want to mutate, and it will prepare all the calculations. You just have to run them. And afterwards, it does the analysis, and it will show you. We'll have like little flags. It will show two things. It will show. So here you have the color gradient scale for the mutations. So you have like you're going from very favorable mutations in blue to a very unfavorable mutation in red. That's what you have here. And then you have these little dots, like just traffic lights, basically telling you, well, this calculation, I think it's not converged, So just by looking at the systematic error, looking at the hysteresis, this calculation in red definitely not converge. You better redo it. In green, you're pretty safe. In orange, be careful. But the idea was like basically to take you by the hand all the way through, from the construction, from the setting up of the simulations, all the way to the post facto analysis of the simulations. Okay, so now we have less than an hour, so I have to rush. We're going to talk about geometrical fringe calculations. I'm sorry, I'm very talkative. And I'm saddened actually to start this with this first slide, talking about reaction coordinates and mentioning David Chandler, who worked for a long time on this. He passed away yesterday. So David Chandler, you may know him from his statistical mechanics book, very famous statistical mechanics book, and also for his work, his immense work on transition path sampling. If you heard about the word transition path sampling, that's David Chandler in Berkeley. And I want to talk about the notion of reaction coordinates and perhaps try to entice you to use the proper vocabulary. When we talk about reaction coordinate, what are we talking about really? I mean, reaction coordinate, the true reaction coordinate, is usually refers to a mathematical object that lives in R3M. So it's a pretty complex thing. It's not. Sometimes we hear, oh, my reaction coordinate was Z. The direction is with Z. No, reaction coordinate is much more complex than that. If you think about, for instance, this guy here, this is a peptide nanotube, so made of cyclic peptides that are tied and connected through a network of hydrogen bonds. And you can see here a close-up on an ion, a chloride ion translocating in this peptide nanotube. You could say, of course, I mean, my reaction coordinate is the long axis of this hollow cavity, but that's not true. I mean, it's a reduction of the true reaction coordinate. There are many other degrees of freedom that participate to this reaction coordinate, chief amongst which the coordination of the ion by the different amino groups of the cyclic peptides that really contributes to the free energy, right? So you can make your reaction coordinate model a little bit more sophisticated by, instead of considering just the long axis, you could also consider the radial direction. The reason you want to consider the radial direction is very simple. If you use just the long axis, but you want to drag reversibly the ion along the long axis of the nanotube, right? But at some point, it will be chelated by the amino groups, and these amino groups will kind of thwart kind of hamper the diffusion in the nanotube. Okay, so one way to prevent that is also sample in the orthogonal direction, what I call rho, and as you can see, you better do that to actually, as you can see here, if I look at the motion of the ion, it's not a rectilinear motion; it's actually zigzagging, which is kind of also can be seen here by this energy jumps in the free energy, in the two-dimensional free energy profile. So really careful when you say, well, I use that as a reaction coordinate. Reaction coordinates are actually much more complicated than what you think. What you're using, I like to use the word transition coordinate. It's just like or reaction coordinate model. Why are people like David Chandler very adamant about the use of the proper vocabulary? Well, there is one reason. You can use any transition coordinates if you're just interested in thermodynamics. We said that as a preamble to this lecture, that the reaction pathway doesn't matter as long as you are interested in a free energy difference, right? I mean, some of them are more ludicrous than others, but the doesn't really matter through which pathway you go. The important thing is the free energy difference between the two basins. But if you're interested in kinetics, then you're really in trouble, and you better get the correct reaction coordinate, because now we're talking about measuring barriers, and depending on where you go, the barriers can be really substantial, right? So you can make an inference, and basically say, well, I think that this combination of collective variables give me a pretty good representation of my reaction coordinate. Okay, a pretty good model. Okay, and then you calculate your free energy profile, and now we're going to verify a posteriori that my guess was a reasonable one, and this is what we call a committer analysis, and that's also from David Chandler. So the idea here is to run a series of molecular dynamics simulation, and we're going to consider different values of psi, of my reaction coordinate model. So I'm going to place myself here. That would be 0.469. I'm going to place myself here, 0.49. That's really on the top of the barrier. And I'm going to place myself here. And so, as you can see, when I'm on the top of the barrier, I really have like a nice distribution. Whereas when I'm slightly on the left, it's completely shifted to the right. And when I'm here, it's completely shifted to the left. So basically, when I'm on top of the barrier and I'm shooting many trajectories, I have an equal chance to go either on the left or on the right. If I'm slightly on the left, then I'm going back to the reactants. Whereas if I'm slightly on the right, I'm mostly going to the products. Okay, so that's something you want as a good practice, just to verify that your reaction coordinate model is not completely out to lunch. Okay. So on the menu of what we have in NAMD through the CoLVARs, the collective variable modules, we have variables of increased collectivity going from Euclidean distances, something very simple. Projected distances, a distance, Euclidean distance projected onto the z-axis or projected onto the xy plane, to angles, to dihedrals, and then we increase the collectivity. We have RMSDs, gyration radii, and all the way to eigenvectors. So the eigenvector that you can obtain, for instance, from an NMA, network. No, it's not NMA. It's ENM, or elastic network model. Sorry. No, but NMA is. What's NMA?
No more.
No more. That's sorry. Sorry. It's Alzheimer. So one thing that you have to be very careful or pay attention of is these variables, like RMSD, are highly degenerate variables. So think about it in terms of the so-called folding funnels of Peter Walliness. You can have very different conformations. An RMSD is a scalar, but for one particular value of this scalar, you can have very different conformations. So in terms of sampling, you really have to pay attention to what you're doing. I mean, I'm not saying that you shouldn't use these variables, but you have to know what you're doing. It doesn't discriminate very well between different conformations. So you have to be aware of that. That for one value of the RMSD, this is the folded state, and these are an ensemble of unfolded state that can correspond to the same value of the RMSD, but yet they're very different conformations. Okay. Another example to illustrate the complexity of unmodeled reaction coordinates. So we showed recently that in rhotaxanes, are you familiar with rhotaxanes? So rhotaxanes were basically the object of the Nobel Prizes in chemistry this year with Jean-Pierre Sauvage and Stoddard. Those are like these little molecular machines, and rhotaxane is essentially a molecular wire, molecular thread onto which you're threading a cavity, typically a cyclodextrin. And this cyclodextrin, so you can use that as a switch. And so the idea is you have stoppers, and you have stations, and then so along the wire, and in the middle usually you have like a group. So if you have like a cyclodextrin, with the cavity of which is highly hydrophobic, so in the middle of the thread you're using like a bipyridinium, which is like a highly charged group, and so it doesn't like to go over it because it's like an unfavorable interaction. And so these rhotaxanes, these little molecular switches, can be activated through different ways. They can be pH activated, they can be temperature activated, they can be photon activated, and there are different rates, of course. You have like these barriers to cross corresponding to the unfavorable interactions. But what we saw is that as it moves along the thread, it's not just like pure translation. It's a translation and a rotation at the same time. And if you're trying to just simulate the motion of the cyclodextrin along the thread in terms of a pure translation, it's going to be very hard, because you're assuming that you're basically assuming that you're averaging the rotation of the cyclodextrin. And that's not prone to happen, depending on the nature of the cyclodextrin. So you really have to introduce another collective variable to do that. The same thing for something as simple as this small peptide. I'm going to see that in a minute. This is decaalanine. And if you really want to study the unfolding of the complete unfolding and refolding of this decaalanine, you better increase the dimensionality of your reaction coordinator. A simple end-to-end distance is not enough. Yes?
So if you want to simulate one of the cases where you have actually like the reaction coordinates in 2 dimensions, do you have to simulate with two reaction coordinates, or can you like?
It's one reaction coordinate made of two collective variables.
Sure, but do you have to follow that, or can you like only run through one reaction coordinate and evaluate it in the other?
No, the way we do it is we actually mapping the full two-dimensional. Yes.
Oh, okay.
Yes. We're gonna see that in a minute. Okay, I want to also mention something. So since we are talking about transition path sampling, I want to illustrate or give you one method to actually try to guess what's the reaction coordinate, or what's the best model of the reaction coordinate. And one of the methods that is used is the string method, and I'm going to talk about a variant of the string method. So the string method is from Eric van den Eyden in New York, and the variant is actually from the group of Benoit Roux. So this is called the string method with swarms of trajectory. If you want the detail, again, I'm not going to go through this slide. We can talk about it during the tutorials this afternoon. I just want to illustrate it. The basic idea of the string method with swarm trajectory is the following. So let's illustrate it with a very simple example. This is dialanine. This is the free energy landscape of dialanine, which has like these two free energy basins corresponding, so-called C7 equatorial, C7 axial, because it forms like a pseudo C7 seven-member ring, whereby the oxygen here interacts with the hydrogen here. Okay, So we have axial, we have equatorial. We're gonna guess. This is a very rough guess. This is just a straight line going from C7 equatorial to C7 axial. This is my guess string. So I prepare my string and prepare the beads here along the string, which we call them images. This is just a linear combination of the phi and psi angles. So I have like here, we have like something like 20 images. So now what I'm going to do here is for each bead, for each image, I generate, so I do a restrained MD at this particular values of phi and psi, equilibrate, and then I will generate a swarm of trajectory for each image. Okay, so those are very short simulations, very short. And from these simulations, from this swarm of trajectory, I calculate an average drift. This average drift will help me actually infer the direction towards which I have to evolve my string to get the minimum action, the minimum free energy pathway. So I do that iteratively. So I do image by image, or I can do that also in parallel. There is no actually requirement to do it in parallel, but can do it in parallel. So I do that for the 20 images, and that's my first iteration. Then I get the different drifts. I evolve my string. I reparameterize the string. It's important that the images are equally or they are equidistant, and then I get the next string, and then I go again and I regenerate new swarms of trajectories. Okay, so to show you in a little movie how things work. So this is the starting point, and now I'm going to evolve my string. So you can see that this is a poor guess because I'm going through the maximum of the free energy. I don't want that. Nature hates to go through high energy barriers. So I'm evolving this, and slowly but surely, it will actually go through. It will find a passageway that corresponds to the minimum effort. Okay. And yes.
Can I just make a short question? You mentioned that for each beat you do a strain simulation, or is it just a regular simulation?
Yes, to prepare them, just to prepare it. And now, the master is back. So this is actually no, not yet, not yet. So yeah, what do we do with that? What do we do with this string? So I have my string, so it's optimized now. Well, I have some variables which are called path collective variables, and that has been cooked up by the Parinello group to basically follow the string and calculate the free energy along the string. Now you have to be careful because. So we try to follow the string, but depending on the shape of the string, maybe we can go astray and far actually from the string. So there is a secondary variable that you can introduce, which basically you can see as doing sampling in a tube that embraces the string, and that kind of you can see that as a zeta. You can see zeta as a restraint to prevent sampling to go too far from the string. So you basically generate a two-dimensional map, right? And then you integrate in the other direction to get the free energy along S, the actual collective variable for the string. And now, not yet. So this is our string, and this is the kind of free energy profile that you get. I just want to emphasize again that when you're just interested in a free energy difference, it doesn't matter which pathway you choose. So if you just take a two-dimensional free energy map, if you do a real free energy calculation in 2 dimensions, phi and psi, and you integrate between the two basins, you get 2.5 kcal. And it so happens that if you do the path collective variable, you also get a free energy difference of 2.5 keV. Okay? So far, so good? So now, for the master. This is what you're seeing here is the so-called chromatophore, which you may have heard of, which is the apparatus that is used by nature, by certain bacteria, Rhodobacter spheroides, to transform light energy into chemical energy. And what you can see here in the chromatophore is ATPase, and ATPase is the machinery, is the molecular motor that is used for synthesis of ATP from ADP, or it's a reversible motor. It can also be used for hydrolysis of ATP into ADP. So what Avicek did is actually use, and I think that's the most heroic use of the string method so far, is the application of the string method to study to define the transition pathway corresponding to the hydrolysis of ATP into ADP. So what you can see here, this part is actually what we call the crown or the A3B3 ring, and as you can see the breathing. Just to give you the little detail, so you have like three AB interfaces. So constantly they are one of them contains ADP plus P, one of them contains ATP, and one of them is empty. And it kind of so when ATP is hydrolyzed into ADP, then the product goes away, then it becomes empty, waiting for ATP to come in, and so on and so forth. It works by a cycle of 120 degrees. And in this process, you have like a lot of breathing, like opening and closing of these interfaces, which in turn promotes the motion of the, which you can see here intermittently, the shaft. So the shaft is this also called the domain here, the central stalk, and this central stalk is the thing that you can see rotating. Right? Okay, so now that we have defined collective variables and reaction coordinates, what do we do with them? So you have again on the menu a number of methods that you can use. The first class of method is basically belong to the same class. Actually, it's the same method. Metadynamics, in fact, has ancestors. So metadynamics was proposed in 2002 by Michele Parinello, but the same method actually existed, was cooked up in 1995 by Helmut Grobmüller, and at the same time by Wilfried von Ginstern, with the name local elevation or conformational flooding. And this is basically what you're trying to do. You're basically trying to flood the free energy landscape using some Gaussians. And basically the idea is at the end, once everything is flooded, you evolve, and you keep, of course, a memory. You have a memory kernel of what you have flooded, and basically at the end you evolve on a flat free energy landscape. Different idea, although you're basically trying to achieve the same result. These two guys are Glenn Torrey and John Vallow. Umbrella sampling, that's a much older method, 1977. What I'm going to show you is the real umbrella sampling, and not what people call today umbrella sampling, erroneously. The original umbrella sampling actually really had an umbrella. Today we don't use umbrellas. But at the time of Torrey and Vallow, the idea was to guess a biasing potential that could help overcome the free energy barrier. So how do we do that in practice? Well, first thing, we're gonna use the Valo and Card idea of 1972, which is essentially the same thing, the same idea that I was mentioning for perturbation theory, which is stratification. We cannot just do a simulation for the entire pathway; that would be like too large, too long. So we're gonna just cut the reaction pathway into windows, and these windows have to overlap. And I'm gonna say why in a minute. Okay, so that's the first stage. So we're gonna define windows, and we're gonna confine sampling in these windows by means of a harmonic potential on each side, by means of a wall. Okay. And now the second part is to define the umbrella. And the umbrella should be exactly, but you have to guess that, should be exactly the negative of the free energy. So that when you add the biasing potential, when you add the umbrella to the actual force field, then the result is a flat free energy landscape. And again, the idea is to evolve on a flat free energy landscape guided by the self-diffusion properties of your system, right? So once you have that, then you can recover. So you get your biasing. You basically histogram. It belongs to the histogram class of method. And so once you have that, so you have your biased probability distribution, and you recover the free energy by taking the logarithm of that, and whatever biasing potential you have introduced in your calculation, you have to remove it from your calculation. Now, why do we need to have this overlap between windows? Because we're dealing with the free energy, and the free energy is defined up to a constant. So it's very possible that when you recover the free energy in window 1, you will have something like this, and in window 2, you will have a jump, the second part of the free energy, and then maybe another jump. So you need this overlap region to actually paste things together, which you can do by hand. You can write a little program that will minimize the curvature in the overlapping region, or you can use the so-called Fehrenberg-Swenson equations, which are self-consistent equation, also known as weighted histogram analysis method, or WHAM. For your information, if you heard about M-bar is very similar to WHAM. Those are like also kind of self-consistent equations wherein you just introduce your probability distribution for the different windows and the biasing potential that you've used in the different windows. And you bootstrap that with one free energy difference, and then you solve iteratively these equations. So that's the real umbrella sampling. Now, what people call today umbrella sampling is a super stratification of the reaction pathway. Now we're going to use tons of windows, very small windows usually. So if this is a distance, we're using like maybe 1 angstrom windows that are also overlapping. The reason you use these very small windows, then you don't need to define an umbrella, because within one window, the free energy difference, I mean, if you look at the change in free energy, it's less than kT, so it's something that you can easily sample with Boltzmann sampling, right? So the only thing you have to do here is just introduce the confinement potential, and that's enough. And then you feed that to the WHAM equations, and you're good to go. Another method that I want to talk about, yes?
Because back in the day, then how did people perform effectively, like now, of course, continues to define the stratification?
So there were intermediates. I mean, there were variants of the umbrella sampling between then and now. I mean, for instance, a good example is Martin Karplus, 1997, with an adaptive umbrella sampling. So it was still the idea, the Torri-Valo idea of guessing the umbrella, but guessing it iteratively. So basically running a simulation, getting the probability distribution, and seeing if you get a uniform, because that's ultimately that's the criterion. What you want to have is when you add the biasing potential, to the force field, you want to get a uniform probability distribution across the window. If your probability distribution is completely skewed, it means that you completely messed up your guess of the biasing potential. And so iteratively, they just modify so if you use, for instance, a ramp, they modify the slope of the ramp and run again a short simulation until they actually get so you can find that it's Bartels and Karplus 1997. That's the adaptive umbrella sampling. So this is another method belonging to a totally different class of methods. So umbrella sampling, histogramming. This belongs to the class of gradient-based methods. So the idea here is you define your reaction coordinate model. So what you see here is the reversible unfolding of decaalanine. I'm going to replay the movie below. So the idea here is we take the reaction coordinate here, the model side. We're gonna discretize it into small boxes, so small increments delta psi, and the idea is that each value of psi that we sample, we calculate the force exerted along the reaction coordinate model. Okay? The thermodynamic force, this force. And so we basically we just increment a counter, saying, okay, we've been to this value, we stopped at this value of psi, and this was the value of the force. Then I solve my equations of motion, and then maybe I find myself in the adjacent value of psi, and I increment the counter, and I store the value of the force, and so on and so forth. At the beginning, I'm just doing this. This is pure Boltzmann sampling. At some point, I will reach a certain value, a certain threshold for the number of samples per bin, per value of psi. Then I calculate this expected value. And that expected value of the force, by definition, is equal to the gradient of the free energy. Right? And that will help me overcome the free energy barrier. That's what you saw in the movie. I mean, maybe it was a bit too fast, but so at the beginning, I'm in this little valley here, doing Boltzmann sampling. Then I'm applying the bias, and boom, I end up in that region. And then progressively, things arrange themselves, and I converge towards the free energy, the actual free energy profile, with a so-so uniform sampling. If you want to make an analogy, so metadynamics will be flooding valleys with Gaussians. This will be, you could see that as a bulldozer crushing snow until you have like a flat free energy landscape. And again, you're evolving on this flat free energy landscape guided by your sole self-diffusion properties. So if you want to do, so this was the adaptive biasing force method, and so if you want to do a free energy calculation with the adaptive biasing force method, you need, as usual, the files from an equilibrated simulation. You need a colvars.in file, so that's the file where you define your collective variables. You need, of course, a PSF file, a NAMD file, and then as an output, you will get the usual NAMD output, and you will get a state file and a trash file. The state file is a file that you can use to restart your simulation. It will write the last state, the last value of the gradient, the last value of the counter for different bins. The trash file gives you the actual value of the reaction coordinate model as a function of time. You can also add the value of the force acting along the reaction coordinate model. And then you have like specific file. You have a grad file, a PMF file, and a count file. So the PMF file contains the potential of mean force, the free energy change. The grad file contains the gradient, and the count file contains the number of samples per bit along the reaction pathway. Now, I want to impress upon you that as of today, you will get a PMF file only if you have a one-dimensional free energy calculation. If you have a multi-dimensional free energy calculation, you need to do a post-processing. We do not calculate on the fly. We do not regenerate on the fly the multi-dimensional free energy landscape. You have to do that a posteriori based on the gradient file, and it does like a Monte Carlo calculation, Monte Carlo integration to get the multi-dimensional free energy profile, free energy landscape. So the example of unfolding of decalanin, which you have to work on, or which you may choose to work on this afternoon, if you wish it so. So this is the unfolding. This is the free energy. This is the free energy landscape. Just to give you an idea of what I was talking about in terms of applying the force. So we're sampling the reaction coordinate model psi, so that the end-to-end distance going from 12 to 32, discretized in different bins, and here I'm showing the probability distribution of the force, so that I get, I'm storing the force for different values of the reaction coordinate model. So at A, at B, and at C. And what you can see, if I'm at A, it's Gaussian distributed, and the peak of my Gaussian distribution is slightly on the positive side because my free energy is going down, right? And if I'm at B, it's slightly on the negative side because I'm going up in free energy. And when I'm at C, well, it's almost at zero because it's almost like a flat free energy landscape. One thing I want to mention, when you're doing this calculation, you want to be careful about the contamination of other sources, or other forces, and in particular, holonomic constraints. So if you are defining the transition coordinate, you have to be careful that they do not involve atoms that are part of shaken, rattled degrees of freedom. So for instance, in the case of decaalanine, if you want to take, for instance, as a transition coordinate, the first C alpha and the last C alpha, well, they are connected to hydrogens. And therefore, if you have shake rattle going on, CH is frozen. And therefore, you will have contamination of the biasing force by this hard degrees of freedom. Okay, so that will generate an erroneous potential of mean force. So either you turn off shake rattle, or what you can do is you take the whole thing. Instead of taking just the C alpha, you take the C alpha and the H alpha. And in this case, you're good to go. You remember the example that I was giving about the hydration of ethanol from an alchemical point of view going in the vertical direction. Now you can do the same problem and verify that your thermodynamic cycle closes by doing the horizontal transformation. Of course, the lower one, nothing to nothing, is nothing. So to do that, well, you can define as your transition coordinate the projected distance between the center of mass of ethanol and the center of mass of the water lamella projected onto the z-axis, right? And that will give you a potential of mean force. So this is This is the colvar, the collective variable that you define. Oops, too fast. But basically the idea is, so you get your potential of mean force, and so you get two plateaus, and the difference between these two plateaus is the hydration free energy. Okay. Now, good practices. If you want to measure binding free energy constants from the point of view of geometric transformation, you will see often in the literature the application of this formula that goes back to an article of Attila Szabo back in 1982, which is basically the integration of the potential of mean force, normalized integration of the potential of mean force over this area here of association, which corresponds to the association. So, like here, for instance, you have like two benzene. I want to put a caveat emptor here, or big warning sign. Applying this formula is certainly fine for something as simple as benzene. The reason is very simple. This formula, not written, but this formula supposes that you're basically averaging over all possible orientations. Right? So in the case of benzene, I mean, the reorientational time for benzene is about 6 to 12 picoseconds, depending if you're looking at the C6 axis or the C2 prime axis. So you can do that. If you do like multi-nanosecond simulation, you're good to go. But unfortunately, you see a lot in the literature people applying the same formula for beasts as big as Barney's bar star. And of course, this is not going to work because, and the argument is the following. The argument is, well, in the course of a nanosecond simulation, I don't see them tumbling, therefore I can do that. But no, I mean, it's not because you don't see them tumbling that the tumbling doesn't exist. So assuming that you have averaged over all possible orientation of protein 1 with respect to protein 2 is just erroneous. So you need to do something different. Now we're going to talk about this. So we're going back to the protein-ligand problem that you're already familiarized with, but this time we're going to see it from a geometric point of view. And so the first step, as before, is freezing the conformation of the ligand with respect to that of the native state. Right? So I'm freezing it. Then I'm also defining again the position and the orientation of the ligand with respect to the protein by introducing groups of atoms in the protein. So 3 groups of atoms in the protein, 3 groups of atoms in the ligand. And so with these 3 groups of atoms here and there, I can define my usual Euler angles and my 2 polar angles, theta and phi. And so I have to calculate potentials of mean force for these different degrees of freedom. So it kind of works like Russian nested dolls. So here's how we do it. So we start with the complex, the protein-ligand complex, and I'm freezing the conformation of the ligand. So basically, I'm applying as a collective variable the RMSD, and I'm forcing the RMSD. First I'm calculating the potential of mean force with respect to the RMSD. And that's where you have to pay attention because of the degeneracy of the variable. Now that I have this potential of mean force, so that's my first potential of mean force, the one on top, then step 2, I'm freezing the RMSD. I'm forcing the conformation of the ligand to be that in the native state, in the bound state. Okay? And now I'm calculating the potential of mean force with respect to the first Euler angle. Having done that, step 3, I'm freezing the first Euler angle and the RMSD, and I'm calculating the potential of mean force of the second Euler angle, and so on and so forth, all the way to separating the ligand from the protein. That's the magnum opus of the calculation, the more costly part of the calculation, separating. Because here again, using just the distance between the two guys as my transition coordinate is kind of a rough approximation of the actual transition or actual reaction coordinate. I have all these other degrees of freedom that are kind of thwarting impeding the separation, and namely all the favorable interaction, the salt bridges that exist between the ligand, the hydrogen bonds that exist between the ligand and the protein. Okay. And once I have that, I need two more things. I need this, which is again just like in the perturbation theory, which is the potential of mean force for the RMSD in the bulk state. So what's the reversible work that I have to supply to the system to maintain the conformation, that of the bound state. And then I have these analytical terms corresponding to the translation and to the rotation of a rigid body in a bulk environment. And once I've done that, then I just do the bookkeeping and I can calculate my binding constant. Okay? And so this, you can of course apply it not only for protein-protein, but for protein-ligand, but also for protein-protein. So some good practices. So I already said that. So you want to decouple your psi, your transition coordinate from any constraints. As a matter of principle, you always want to stratify. You can demonstrate that mathematically. I can refer you to the demonstration that we did using a very simple Brownian motion. You can show that if T0 is the time that is needed to sample the entire reaction pathway, and T prime I is the time needed to, when I say sample, I mean like to converge, to get a converged free energy calculation. And T1 prime is Ti prime is the time required to get a converged free energy in window I. Then you can demonstrate that T0 is always greater than the sum over I of Ti prime. So you want to stratify. You want to stratify. There are cases where you want to turn to an alternate formulation of the adaptive biasing force. For instance, when you have restraints that are coupled to your transition, say restraints, not constraints. Restraints coupled to your transition coordinate. That will be the case, for instance, when you're doing this protein-ligand calculations, where you have, like, let's say that you separate the ligand from the protein, but you have the conformation that is restrained, the Euler angles that are restrained. So in this case, you want to turn to an extended Lagrangian formulation. Just in a nutshell, the idea is now you're no longer tracking down the transition coordinate, you're tracking down a particle, a fictitious particle that is attached by means of a stiff spring to the transition coordinate. And now it's on the fly, so you get immediately the result, the correct gradient. So that's it. Yeah, so that's for the on the fly. I will pass this slide. It's much useful. So now safeguards. When you do this free energy calculation, I told you that these ABF calculations, I told you that you want to stratify. So it means that you will generate for different windows, you will generate different gradient profiles. So by virtue of the continuity of the gradient across the transition pathway, so the gradient is a continuous function of psi or of z in that case. You want so you don't need, unlike in umbrella sampling, which deals directly with the free energy. Here we're dealing with the gradient, so you don't need to have any overlap between the windows, because your average force is continuous across the reaction pathway. So you really want to have a continuous, verify that your average force is continuous. And if this is the case, then you just paste the different pieces, integrate, take the negative of that, and there you go. You have the free energy profile. Free energy profiles, just like in perturbation, in alchemical transformation, in perturbation theory, you want to provide them with an error bar. And, well, the mathematics exist. I'm not going to lie to you. It's a real pain in the ass to calculate, because you have to calculate this correlation times, because when you're doing MD, your data is highly correlated. So it's not like you're not dealing with n samples, but you're dealing with n sample divided by the correlation length of the series. So, but there are tricks to do that. It's not like you're completely abandoned in terra incognita. There are tools to do it, but it has to be done. It's something that you want to, when you provide your fringe profile, you also want to provide error bars. One way to assess convergence of your fringe calculation, it's a cheap trick, but it's pretty informative. Instead of running a very long simulation, a very long fringe profile calculation, break it into subruns, and just say that my last subrun is the converged one. Just making this assumption, and then you calculate the RMSD on the gradient with respect to the previous subruns. And so if you have something that is that decreases asymptotically, then you can say, I'm probably, like in this case, it's pretty good shape. If something that goes like this, not so good. So probably I need some more sampling. Okay. What about non-equilibrium work, computer experiments? Can I have 5 more minutes? Is that okay? So what about non-equilibrium work experiments? So I mentioned that at the beginning. So you can reconcile non-equilibrium work experiment with free energy by virtue of the Jarzynski identity, which relates the free energy to an ensemble of realization where you're pulling experiments. On the paper, it converges formally. In practice, you want to be in a near equilibrium regime. That's very important. And you need to run quite a bit of independent simulations to get a good estimate of this. Just like the bar estimator, you have the Crookes theorem, which does pulling in both directions, and you can combine the two simulations to get a better estimate of your free energy, just like a Bennett acceptance ratio. I'm going to pass on that. I'm going to go directly to more interesting things. Ongoing developments. I need to mention that. Very important. So you remember I was mentioning some of these calculations are plagued by ergodicity problem. Like for instance, you are stuck in one conformation, but the problem is that other conformations are important for your free energy. So what you can do is the following. So you can take advantage of the massively parallel architectures that we have today and replicate your system. So imagine that you're interested in a hydration free energy. You just replicate your system so at the different values of lambda. So this is just a very simple example, but you can see at different values that make my solute disappear, right? And so you propose some swapping of the configurations for two different adjacent values of lambda, and then you have your usual Metropolis Hastings criterion, verify that it works. So you either accept the swap or you reject the swap. Is this acceptance criterion? And the idea is, as you progress in the simulation, is basically make configurations at high value of lambdas accessible to configurations at low value, kind of exchange all across the reaction pathway. Now you can even make that a little bit more complicated. So in addition to propagating in lambda, you can also propagate in temperature. Why would you want to do that? If you want to calculate entropies, for instance, using what I was mentioning before, the derivative of the free energy with respect to the temperature, that gives you the variation of entropy. So, and again, here you can swap. So what we do with this algorithm is we swap alternatively. So we swap in lambda, and we also swap in temperature. So one time we swap in lambda, one time we swap in temperature. And again, we accept with the same kind of Metropolis Hastings algorithm. Okay. So all of this is available, by the way, in NAMD. So I could also mention that. So in the same line, this ergodicity problems. So imagine that you want to progress. That's basically the problem that I already mentioned with the peptide nanotube. Your transition coordinate is psi. You want to progress along psi, but you have this orthogonal degree of freedom. That's kind of a problem. You have this hidden barrier along zeta. You're working along. I mean, your ABF or your umbrella sampling is helping you alongside to go up the hill, but remember this formula. You have this ensemble average at constant psi, and at constant psi it means that you have to sample not only this value for one value of psi, but you also have to sample that value. And the problem is that you have this high barrier. So what can you do for that? Well, one way to solve the problem. So if you use just one walker, you're basically staying in one valley, and you're stuck in that valley, right? So the idea is, so it will never. I mean, crossing the barrier would be a super rare event. So what you really want to do is actually propagate replicate that walker, and so now you have multiple walkers living their happy life on the free energy landscape and exchanging information every now and again about the surface, about the gradient that they see, right? And then you can even make it more complicated introducing some Darwinian selection rules. So we kill the bad ones and we promote the good ones. So the bad ones are the ones that don't diffuse very far, and the good ones are those that really covered a good stretch of the free energy landscape. I think I want to stop here. Do I want to stop here? Pretty much, yes. I mean, we can talk about it this afternoon. I had one extra slide about going beyond the thermodynamics. I mean, now we can also use these free energy calculations to do kinetics. So for this afternoon, this is what you have on the menu. I just want to say one word about that. You have like some very basic introductory material, one for geometric calculation with ABF, one for alchemical calculation. I know I was eavesdropping yesterday, and I know that some of you are interested in binding free energy. There is one tutorial for binding protein-ligand binding free energy, but if you've never done any free energy calculation before, I would highly recommend that you don't go here, because then you will really hate me. Just go there first. I mean, you don't need to do the whole thing, but just do one or two exercises in this one and in that one. This tutorial is protein-ligand binding free energy from the 2 points of view, the geometric route and the alchemical route. And finally, this one is a little bit more advanced. That's using the string method. So it has 2 parts. The first part is actually finding the transition pathway, and the second part is calculating the free energy along the transition pathway. Yes?
If you don't know the reaction coordinate, but you know that you are represented by 2 dimensions, is it more convenient? If you're only interested in saying calculating the barrier height, is it more convenient to do the 2-dimensional dynamic study or something like an ABF, or to do?
Yeah, well, in this case, you're going to compare actually the real thing, because David Chandler showed in 2000 that for dialanine, the reaction pathway, at least in vacuum, the reaction coordinate, the real reaction coordinate is 5 psi. And you're going to verify that you can also use like transition path sampling, and that it gives the same answer, right?
And the times it takes to simulate?
Well, Avicii could tell you that doing like a Schwarzschild trajectories, I mean the string with Schwarzschild trajectories is extremely expensive. So in this case, it's not really worth it. It's more like a proof of concept. But like for more complicated reaction pathway or more complicated free energy landscape. For instance, the example of ATPase, that was done, I didn't say that, but that was done with 392 Cartesian coordinates. So that's a different story. So imagine the size of the dimensionality of the space. So in that case, yes, you have to do that. Yeah, you cannot do a ABF umbrella sampling because you are discretizing the transition coordinate. So you would have to fill these little boxes. So when it's one dimension, you feel like it's pretty easy, pretty fast. Two dimension, now you have like all these little squares. Then in 3D, there are all these little cubes. After 3D, it's pretty much toast. So then you really need to do transition path sampling and then do a reduction projection into 1D with something like the string method. Yep.
So in replica exchange,
Yep.
so how do you swap the two systems?
How do I what?
Now, what is the criteria to swap the system?
To swap. Oh, it's completely random. So what we do is we select in the process. So we have these different boxes, these different replicas that are run for different values of the Hamiltonian, or different values of lambda, right? And so we just select randomly a pair of boxes, but adjacent boxes, and we propose a swap. And then with the Metropolis Hastings criterion, we either accept the swap or we reject the swap.
What is the criteria to accept the swap?
Oh, it's just energy based on so the energy of the box with so you have to. It's a combination of the configuration of box I and the value of lambda I, the coordinates of box I and the value of lambda j, the coordinates of box j and lambda I, and the coordinates of lambda j, coordinates of j and lambda j. So that's you have like energy for this, the energy for this four combinations.
You mean that if they are in the same state of energy, then they are going to have the same confirmation?
Pardon me?
If they are in the same state of energy, then they are going to see the same confirmation.
Conformation.
The three-dimensional space, orientation or something. They belong to same energy then. That's what they
No, they have different energies. Why would they have the same energy?
Then we cannot swap, right? So they should be in level with the energy. Then the probability goes 1. So
Are you afraid of the acceptance?
Yes.
Yeah, well, that's why we choose contiguous boxes. And again, we this is the same problem as what I was mentioning at the beginning. You need your perturbation to be a perturbation, not a huge change not like a substantial change in of your system, right? So that's why you need. Yeah, it's important. I insist that the it has to be adjacent boxes. It's not like lambda equals 0 and lambda equals 1. That, of course, your acceptance rate will rapidly tend towards 0.
that's a rare event, right?
Yeah.
And if you go with respect to temperature swapping,
Yep.
so how do you scale the temperature with respect to your sample?
How do I scale the temperature?
Is there any factor which brings the number of temperature range with respect to the case of problem? Suppose if I take theta.
Yeah. So the choice of the temperature increment is actually a problem. It's a problem. If it's too big, then the linear approximation for calculating delta S is no longer true. If it's too small, then your free energy change is on the order of the error of the calculation. So it's I can point you. I mean, we worked on that. I mean, we have a couple of papers on that. It's the choice is it's a delicate choice. It's something that you need to think about.
So I have read, I'm sorry, I have read somewhere through. So it depends upon the number of atom of the case. Like if you select the protein, so take the number of atoms. So there is some nearest prime number. I forgot. Read long back.
Well, to tell you the truth, I mean, we haven't done protein yet. We still at the level of very very small solute. I mean, when it comes to calculate the entropy, so we've done very modest methane dimerization. We've done ethanol hydration, but still, even for these guys, it's very delicate choice. I mean, for the reason I was mentioning, like too large is not good, too small is not good either. And you have to find a regime of delta T that is kind of acceptable. Any other question? I mean, you can mull this over during lunch, and I'll stay with you in the afternoon.